Welcome everyone to lecture number 9 in my reckoning. I think if my count is correct, maybe it isn't, but yeah. So where are we so far? So as you can see behind me, so far what we have done is we've focused on physics-informed neural networks of pins, and we have looked at algorithms. And in the last lecture, what I tried to give you was some theoretical insights, right? And the main idea is to see when pins work and when they don't work, especially when they don't work. As you will see today, there are many, many conditions, many circumstances, situations where they don't work. And I think we have a good understanding of that. And so that's the main goal today. So today we are going to look at some further theoretical insights into why pins are going to fail, right? So by the way, just for the people in the room, is it okay when I'm highlighting on my notepad? Is that okay? Or okay. So otherwise, because if I use a pointer, then people on Zoom, they can't follow. So I'm sort of constrained to do this. Okay, so let's recollect what we stopped at in the last lecture, which was online. So first of all, we have some abstract PDE. So this could be, for instance, a heat equation. We are going to see the heat equation again and again today. So this is the heat equation, for instance. So this is the differential operator. And all the sort of information, the inputs to the problem, I'm measuring in terms of, or I'm giving them, prescribing them through this input here, F. This is the source term, the coefficients, initial conditions, boundary conditions, and so on. And the idea is that given a F, we have to find U, right? So this is the rough idea, is that given a F, we have to find U. And to do this, we are going to use pins or sort of physics-informed losses, physics-informed neural networks. And just quickly, we have a neural network, so U theta. And instead of directly having labels to supervise the data on, what we do is that we compute the PDE residual, because that's the only information that we have. This is the residual of the PDE, and we compute it. We can compute it at any point in the domain because of automatic differentiation, finite differences, whatever you call it. And then we want to minimize the integral here. Of course, the integrals can't be directly computed, so you have to rely on a quadrature. So this is going to be our loss function, right? So this is L of theta. Sorry. Why didn't that work? Yeah, L of theta. And we optimize it with whatever, some variance of the stochastic gradient descent method. So this is pins. And what we did in the last lecture was that we sort of developed some sort of framework to analyze pins. And to that end, so this goes down to this paper I wrote some years ago. And essentially the idea is the following, that the point is all the time we have to work with three objects, right? So one is the training error. This is related to the loss function, right? This is essentially the square root of the loss function, L of theta. Then this is the PDE residual. This is precisely the PDE residual, this object here, as you can see. So this is often called as generalization error. So you should think of it as a PDE residual. And the last object here is the total error. And the total error is given by this quantity here. This measures the mismatch between what you compute with the pins and what the actual ground truth is, what the solutions of the PDE are. And the point was that as long as three conditions hold, this program works. And what are those three conditions? The first one essentially is this, let's use a different highlighting color, is essentially the smoothness of the exact solution. So as long as the exact solution is smooth, in principle, and this is very important because you'll see that in practice, there are formidable difficulties in doing it. In principle, we see that both these objects, the residual of the PDE, this object here, as well as the training error or the loss function, these can be made as small as possible because the exact solutions of these can be made as small as possible. You can estimate them. So essentially, this can be made as small as possible because you can make the neural networks, in the space of neural networks, you have some closeness, some approximation to the exact solution of the PDE. So in principle, this is a well-posed or a feasible problem. However, in practice, we don't have access to the exact solution. That's the whole point of pins. We have to infer them through the indirect information that is given by the PDE. And to do that, so we said that there are two structural conditions that one can use. So first is what is called the coercivity. This is, as I said in the last lecture, this is some sort of a stability condition. So this tells you, if you remember, so this was essentially U minus U bar in some norm. is less than or equal to C of u bar, u hat in this case, du minus du hat. Okay, this didn't even fit. So never mind. Okay, so it tells us that if you change the inputs to the PDE in a small manner, the outputs of the PDE change. So some sort of stability, or this is often called as coercivity. And this is essential in order, once this is there, I had this little argument last time, which convinced you that if this is the case, then the total error can be bounded in terms of the PDE residual, right? And once you make the PDE residual small, the total error is going to be small. And of course, we don't have control on this. We don't have a handle on this. We compute it with quadrature. So one can use some sort of quadrature, random sampling, quasi Monte Carlo, whatever, in order to sort of estimate it in terms of the training error. So at the end of the day, we are given with an estimate, which looks something like this. What does this estimate tell us? This estimate tells us that if the training error is small, and this is a big F, so this has to be small, and this guy has to be, if you have sufficient number of quadrature points, then the PDE residual itself is going to be small. And once the PDE residual is small, if the PDE is coercive or has the stability properties, you can leverage them in order to make the total error small. So this is, I keep on repeating, that there are many sort of links in this chain, right? So one link is that you should have sufficient number of quadrature points. And that depends on the dimension, that depends on the smoothness of the function, and so on and so forth. Then you should have sufficiently low training error. And later on, after the break today, we are going to see whether this can be done or not. And finally, you should have some nice properties of the PDE that allow you to make this small residual into a small error. Okay, so this is sort of the basic algorithm. And what we are going to do in the first part of the lecture today is to work out some simple examples to see whether this is true or not. And already you'll see that this gives us a lot of insight into what is going on. Okay, so this is where we are, and this is where we are going to start with today. Are there any questions from within the room? No? Feel free to ask, or people on Zoom, if you have any questions, chime in. You can just ask it through the chat function, the chat button. Okay, if not, let's do some concrete examples. And I picked up some examples which are sort of illustrating the breadth and depth of PDEs. The first example is what is called Kolmogorov PDEs. They look complicated, but they are actually not that complicated. So the point about Kolmogorov PDEs is that they include the heat equation. So this is, of course, what you have already seen. So the heat equation is essentially UT is equal to Laplacian of U. So this is the simplest. And let's see why this equation is related to this equation here. So all that you have to do is to take the transport term. So this is what is called the drift often. If this is equal to 0, then this term, of course, vanishes. And if these guys are just identity, this is what is called the volatility sometimes. So these objects are identity, then you'll just get the trace of the Hessian and you get back the heat equation. So this is the simplest example of a time-dependent PDE that there is. And it models various things, diffusions, mixing, Brownian motion, and whatnot. And then the reason why we wrote it in this elaborate form is because in option pricing, so this comes from finance. So what you do is you have a very famous PDE that governs the prices of options, European options. And this is called the Black-Scholes equation. Many of you might have heard it. It's a Black-Scholes equation, and the Black-Scholes equation is also in this form. It is a particular example of this. So all that you do in this particular case is that, so the drift here, this is affine. So this is simply mu of xj. Mu is often called the interest rate, right? So this depends on what the central banks or the banks are going to give you in terms of money. So that is just a very simple term here. And then these objects here, these so-called correlations, these are given in terms of what is called volatilities. And you can see that there is some terms which are looking here. So this is also a fairly simple term. Let's wait for the ambulance to go. Yeah, so often in a basic PDE or a basic engineering class, you have seen the heat equation. You've probably also seen the Black-Scholes equation. These are all in this very general form, okay? But essentially what you can think of them is some generalization of the heat equation, okay? With some additional terms thrown in, which are, let's say, mild mannered. In fact, you can transform one into the other. But the main point somehow in these problems often is the heat equation is very easy to solve. You can use a finite difference scheme, and as I showed you a few lectures ago, and you get a very accurate solution. So what's the caveat? The caveat is that these equations, particularly the Black-Scholes equation, this can be very high dimensional because D is the number of, so there's the number of stocks essentially, or bonds. So if in your portfolio you have 100 stocks, this is going to be a 100 dimensional equation. Okay, so now this equation is sort of a prototypical PDE, and let us see what happens in this equation. Are these structural conditions fulfilled, right? So let's try to walk you through that. I'm not going to give any detailed proofs, but just give you some nice arguments. So again, this was done a few years ago, and the idea is that first you have to argue, and remember that here the dimension is the key issue, right? Because you want to solve this problem in 100 dimensions, if possible. Even in 1,000 dimensions, people can do it. Okay, so what's the idea? The idea is that if you take a pin, of course, you have to take the tan H activation function. You can take some other activation function like sigmoid. This will also work. The main point is that what you can see is that the size of the neural network, this is going to not depend, because of course you can get a low accuracy if the size of your neural network grows exponentially. But in this particular case, that's the whole point, that you don't have an exponential growth. So this alpha here is polynomial. It's actually depending on, for the heat equation, this is even linear or quadratic. Okay. So the details are not important here, but the take-home message is that by using some deep math, what you can argue is that at least in principle, there exist neural networks which are going to approximate it to sufficient accuracy, independent or polynomially in the dimension and not exponentially. That's why we claim that this overcome the curse of dimensionality. Okay, so in principle, whether you do it in practice or not is going to be different. Now, remember that our objective is not to show this in principle results, but in practice results. And what are these in practice results? That somehow from the structural properties of the PDE, you should be able to read out that if I make a small residual, I get a small, let's say I get a small solution or a small error. And this is based on the stability of the PDE. And this requires a small argument that I'm going to show you in a very, very quickly because it's so easy. So let me just do this. Let's take the one-dimensional heat equation, okay? So you have UT is equal to UXX. This is the heat equation. For the time being, I'm assuming that there are some initial conditions. U at x0 is U bar of x. And U at, okay, so this is, and some zero boundary conditions. So U at 0 equal to U at 1 equal to 0 for all times, okay, for all t. So now remember that the whole point is stability. So let me try to illustrate that. I'll take a different solution. U bar was a bad idea, but let's change that to U hat then. U hat of t is equal to U hat xx plus some, let's say, residual r, right? So this is, for instance, what comes out if you do a neural network. And let's say for simplicity that it has the same initial conditions. U hat of x0 is equal to U bar of x and the same boundary conditions. So the only fluctuation, so you match the initial and boundary conditions. The only fluctuation is that the pointwise residual is no longer 0. Now all that you do is that you take the difference W, which is U minus U hat. And then all that you do is if you subtract one from the other, you take this, then very easy to see that WT is equal to WXX minus R. Okay, something like that. I could have also flipped the signs a little. So let's see if I can erase it. So just because I like a plus here. Okay, it doesn't really matter, right? So now we have this equation, and then from this we have to infer that if the R is small, the difference W is going to be small, right? How do you do that? That's fairly simple. And of course, W at x0 is 0. That is because the initial conditions agree. And W at 0 equals W at 1, which is equal to 0. This is because the boundary conditions agree. So the only fluctuation, the only perturbation between the two equations is given by this term R. And the argument that we're trying to make is that if R is small, then W is going to be small. Because this R is the PDE residual, W is the error between the exact solution and the approximate solution, let's say the pin in this particular case. And then we can very easily argue this. This is just a one-line argument, so that's why I write it. So all that I do is I multiply, let me take black. So WWT plus is equal to WWXX plus RW. This is, I just multiplied. Then I know that this is nothing but dt W squared over 2 is equal to WWXX plus RW, nothing fancy. And this is nothing but less than or equal to WWXX. Plus I use the inequality, AB is less than A squared over 2 plus B squared over 2. And then you have R squared over 2 plus W squared over 2. Okay, so this is straightforward. And then I integrate. So because at the end of the day, the errors are integral. So if I integrate from 0 to 1, this is also very straightforward. W squared over 2 dx is less than or equal to, integration does not change anything, WWXX plus 0 to 1 half R squared dx plus half 0 to 1 W squared of dx. So now it's very simple. As you can see, this is a derivative in time and the integral is over space, right? So you can just flip them. 0 to 1 W squared over 2 dx is less than or equal to. Now here I'll do something interesting, a very, very simple trick. All of you should be able to know this. So I have the product of two functions here. So I can use integration by parts. This is in one dimension, so everyone knows what integration by parts is. So if you take it, then you have minus 0 to 1 of Wx. So you throw a derivative onto W. So it's Wx squared dx. And the boundary terms are going to vanish. Can anyone say why the boundary terms are going to vanish? Because the boundary conditions themselves are 0. If you remember, boundary conditions themselves, boundary conditions themselves are 0. So the boundary terms are going to vanish. So once you have this, then you are almost done because you have half R squared dx plus half W squared. Okay, so now the half can be cancelled. This quantity here is always going to be a negative quantity because, so this entire thing is negative, right? Because this is a positive quantity, it's a square. So this will imply that d over dt of W squared of dx is less than or equal to W squared dx plus R squared of dx. Okay, so this is very straightforward. And then many of you have seen from basic ODEs that we could use something like what is called a Grunwald's inequality. Let me add, so this will imply, I write it on the other page. So let's add a page. This is just some rough work. So what did we have? So we have d over dt of W squared of dx is less than or equal to W squared dx plus R squared dx. And then you have something called the Grunwald's inequality. It's just telling that nothing grows faster than an exponential, essentially. And this will tell us that W squared at t of dx will be less than or equal to essentially 0 to t, 0 to 1, R squared of xt dx dt. Because the initial conditions also agree, so the initial conditions vanish, and you're just left with this forcing term. So as a consequence, you can see that this, if this quantity here, if the residual can be made small, then automatically the error can be made small, right? So this is all that is there. You can see that we have leveraged the stability of the PDE. The details of the proof are not important because it's essentially a few lines, right? But essentially we have leveraged the stability of the PDE and we have concluded that if you have a small residual, then you can have a small total error. Okay, and this is precisely the point that is buttressed through this argument here, as you can see, sorry, this argument here, which says exactly the same thing. That, of course, now there are initial conditions, boundary conditions, and so on and so forth. And because of the boundary conditions, you will have a square root here rather than a square, but essentially the argument is exactly the same. So if the residuals are going to be small, with a constant which is independent of the solution, this is a linear PDE, you get that the total error is going to be controlled. Okay, so this is a simple argument. Now you can argue, why do I need to learn about this? Well, because it's important, right? Otherwise, how else will you conclude that the error is going to be small? So here you leverage the stability of the PDE. Later on in a few minutes, you'll see that there are some PDEs which don't have this property, and then things get iffy, okay? The last point, so this can be done. So as you can see, this part is over. This can be done. Stability implies small error. But what about the quadrature bounds? So because of the very high dimension, you can only use random sampling. Nothing else works. Okay. So you can use random sampling. And then there are some random sampling essentially means that you use what is called the central limit theorem. So essentially, you can show that the PDE residual is given in terms of the training error and the total number of quadrature points, but it's square root of n. Okay, so there is a logarithmic correction because things are correlated, but there is a logarithmic correction, and this is essentially independent of dimension. So now it's independent of dimension. It is always going to be square root of n, or with a correction because there's a log on top. But you know that any power grows faster than a log. So of course, these things decay as n decays. So what have we shown? So we have been able to show that for this particular class of PDEs, albeit very special class of PDEs with wide applications, you have that because of the stability of the PDE, small residuals imply small errors. And because of Monte Carlo, if you take sufficient number of points, independent of the dimension, by the way, this estimate was also independent of the dimension. So all this is independent of the dimension. As long as you have small training errors, which is a big if, then the total error is going to be small. And this is also borne out through actual estimates, numerical experiments. Let me show you this example. So this is in 1D, but it's already telling you what's going on. So in 1D, we can explicitly compute some of these upper bounds. So this is a bound that we just had derived. And you can see that as the number of quadrature points increases, it's not a lot of quadrature points. It's between 100 and 1,000 points. So this quantity decays. And as a consequence, you see that the total error in red, it also decays. Till it saturates, at the end, it has to saturate. So they are sort of following each other as expected. However, the total error is much smaller than the bound. The bound is a very, let's say, pessimistic upper bound. You can see that this is how many orders of magnitude, like 3 orders of magnitude difference between them. So they have the same qualitative information, but quantitatively, you cannot use this bound to say how small the error is going to be. It's pessimistic. But it's nevertheless, it tells you something. It tells you that the errors can be made small. And this is also very interesting because this is the training error. Okay. And this is the total error. And it says you that as the training error becomes smaller, this is a log-log plot. Okay. So here is a log, here is a log. So as you can see that as the training error is small, the total error is going to be small, which is consistent with this inequality. Sometimes the training error can be large and the total error can be small, but never the other way around. It cannot happen that the training error is small and the total error is large. So this has some practical significance, right? It tells us that at the time of training a pen, we can observe that the error is going to be small, the training error, because this we just compute from the loss function. And then we know that the total error is going to be small. So that gives us some confidence on that, okay, our training process has worked. Now we can use this. Okay. And what is also very interesting is that the estimate tells us that it goes like a square root of the training error. And it's indeed true because as you can see, there are 6 orders here in the training error, and there are approximately 3 orders in the total error. So as expected, it also behaves like a square root. So in that sense, quantitatively, the theory is quite tight. But because there is this no curse of dimensionality, this also allows us in practice, okay, these were my rough calculations. This allows us in practice to do computations up to People have done now up to 1 million dimensions, but at least we could do easily up to 100 dimensions without any problems. And you can see that for the heat equation itself, the error increased as you would expect. Remember that there was a polynomial, not an exponential increase, polynomial increase, but it was really polynomial. It was even linear. So between 20 dimensions and 100 dimensions for the same compute time, the error increased by a factor of, I don't know, 4, right? So this is less than even a linear increase. So this is consistent. This was for the heat equation. And for the Black-Scholes equation, the one from the option pricing, it was similar. So for instance, between 20 dimensions and 100 dimensions, and this is roughly, I don't remember now, but let's say 1 hour of training. So we fix the compute, and then we see how the error scaled. And these are the numbers that you can see. So here, even between 20 and 100 dimensions, 5 times increase, the error only increased by a factor of 2. So it's even sublinear in some sense. And similarly, you could do Heston. This is another of these equations, also used in option pricing. Another different coefficients, different formulas, but essentially the same story. Again, you can go without much of an increase in error. It does increase, but very, very mildly. So this tells us that this is phenomenal, right? We can solve a 100-dimensional PDE within an hour of training to 1%, 1.5%, 2% error. So that's somehow very, very satisfactory. There are caveats, which you will see in a bit, but at least for these particular problems, things seem to work. Let's do a little bit more of this. This is a very interesting PDE, another example that I wanted to give with not a lot of details. This is radiative transfer. So for instance, when the energy comes from the sun, it is essentially radiation. It's also very important in climate and so on and so forth. Also in engineering, because there are many, many processes where radiation plays a big role. So essentially there is a PDE. Some of you have seen this probably, but it's a very special kind of a PDE. Let me walk you through. So the quantity of interest, U, is what is called the radiative intensity. Okay, this somehow measures the total amount of radiation at each point and in time. And there is a master equation which governs this. It seems rather complicated, but it is not. So this is, of course, the time derivative. C, as you can imagine, is the speed of light. Okay, because radiation is light essentially, right? So it travels very fast. So essentially, this is a very, very small term because 1 over C is a very, very small quantity. So essentially, in most applications that we are interested on Earth, this term can be essentially neglected. The whole term can be neglected, even though in astrophysics, like when you have exploding supernova, the speed at which these things happen is comparable to the speed of light. So you can't ignore it. Now this quantity, now when radiation comes, you can compute the angle. So this is what is called the angle. Okay. And then this is essentially absorption. The details are not important here. So as you can see that this is a first order derivative here, and there is a source term here, and there is a non-local term. So this is what is called scattering, because radiation is scattered, different rays come and they get scattered. This is scattering. And this is measured in terms of this complicated formula, which tells us that you take all the angles together and you integrate the scattering coefficient. And finally, there are some source terms, right? So how many dimensions are there? So this U is a function of time, in general, but in many, many cases, you can ignore time. It's a function of space. Space is usually 3-dimensional. It's a function of angle. So when you are looking at 3-dimensional space, you have 2 angles. So that's 2 dimensions. And this nu is a frequency because radiation happens at different frequencies. So it's a function of frequency. So this is 1 dimension, 2 dimensions, 3 dimensions, 1 dimension. So in the most general case, it's a 7-dimensional problem. And 7 dimensions, it's just imagine, even if we take 10 grid points in each dimension, 10 to the power 7 is a very, very high number. And essentially, it is difficult to store that kind of, well, in the modern computers, you can barely store them. But if you 10 points is not going to give you any kind of accuracy. So you need 100 points and then you're out, right? So you cannot solve this problem by using traditional finite element methods and so on. And there's an entire subject of numerical radiative transfer that tries to do that. So, but pins, as I said, the good thing about them is that they have this dimension independent property. You never have to generate a grid. You can just use random points. And in this particular case, we don't use random points. We use something called quasi-random points, but that's not a big deal. Similar estimates can be derived exactly because it's a linear equation. So it has exactly the same kind of features, properties as the heat equation. In some limit, it is in fact a heat equation. So one can use that as an argument. But let me show you the examples here, right? So we solved this problem also in 7 dimensions in the paper, but essentially you look at either 2 dimensions or 6 dimensions. So 2 dimensions means 1 space dimension and 1 angle. 6 dimensions means 3 space, 2 angles, and 1 frequency. So this is the harder problem. And of course, we fix the network size. So the complexity is the same, but we changed the training time is the same because we just fixed it. And then we saw how the error develops. And of course, there is more error when you go from 2 dimensions to 6 dimensions. But nevertheless, even for a 6-dimensional problem, which is visualized here using some 3-dimensional quantity, it's called the radiative flux, you can see that the error is only 2%. It took 1 hour. In a finite element code that I had for many, many years, this took maybe 15 days, to get similar kind of errors. So it took only 1 hour. Maybe in modern computers, this will take 7 days, but there are 2 orders of magnitude here, and you can get 2% error. So again, there is in principle mathematical guarantee, which is also reflected in the practice. So high dimensional problems, that's good for this kind of constructions. Good. So let me give you another example. Now let's try to explore some of the negatives, not just the positives, right? So of course, this is the fundamental equations of fluid dynamics. We'll come again and again to these equations. This is the Navier-Stokes equations. And for those who don't know what these terms are, so U is a velocity. So this is a velocity. This is 2 or 3 dimensional. It's a vector. Then P is the pressure. It's a scalar. So essentially, you have in 3 dimensions, you have 4 quantities here: 3 components of the velocity, 1 component of the pressure. Nu is what is called the viscosity. It's a very small number because even for water, maybe it's not very small for the hair gel or something like that, but it's relatively large for a hair gel because it's very viscous. But for water, this is like 10 to the power minus 7. For air, it is like 10 to the power minus 15. So this is a very, very small number. Okay, so you can, in many practical cases, ignore this term. So 4 variables and 4 equations, because these are 3 equations here, and the divergence, because the flow is incompressible, the divergence is going to be 0. So there are 4 equations and four unknowns. All of fluid dynamics relies on this fundamental equation, and we'll revisit it again and again and again. So in principle, you can solve it with finite elements, finite differences, finite volumes, but you can also solve it with pins. And then the thing is, can we go through this entire theoretical argument? It turns out yes, because if you remember that as long as the solutions are smooth, by the way, this is what is in general unknown. And in fact, some of you might know that this is one of these $1 million problems that was posed at the turn of the millennium, that if you can show mathematically that the solutions are smooth, you get $1 million. But people believe that the solutions are in some sense smooth. And nevertheless, if they are smooth, and this is the smooth in the sense that the kth derivative is going to be square integrable, then the pin has a certain size and the error can be made as small as possible, because but just by taking larger and larger neural networks, you can get a small error. Okay, so in principle. But remember that in practice, we have to argue that the total error, this guy here, is related to the residuals. So these are the residuals for the different objects here. And this can be done. This has been done in this paper, for instance. But the point is that the constant here, now remember that in our arguments, we never bothered about the constants because they were linear problems mostly. But in general, you cannot do that. The constants have to depend on the PDE as well as on the neural network. So here, the constant depends on, where is it now? And this is an important caveat. So this quantity here is the curl of the velocity field. Some of you might recognize it as the vorticity. And the whole point about fluid flows in 3 dimensions is that the vorticity can have very complex behavior. So the vorticity in principle can be large. So if the vorticity is larger and larger, then this estimate becomes more and more useless, because even though these quantities can be made small, this is still large, right? And in fact, you can use, so this is an important caveat. So this for nonlinear PDEs, it depends a little bit on the property of the PDEs. And if you take this example where the vorticity is like, this is actually the vortex, which is being advected. At most, this is like order of 3. So this is not so difficult. And this is the ground truth. This is what the pin gives you. These are fairly good approximations. The error is already less than 1%, means this is 1%. So the error is less than 1%. And the bound that we prove is very close to the error. So this is sort of comparable to each other. But in this problem, the vorticity is of the order of 1. Okay, it's not that large. As long as the training error can be made small, the total error is going to be small. Okay, so this is sort of the main point here, that if the vorticity becomes large, you might not be able to do a good approximation. And this is also borne out because now we try to increase the vorticity quite a bit. Earlier, the vorticity was large in the sense that it was concentrated in this little vortex, but now you have larger and larger vortices. So as you can see, this goes all the way from 5 to -5. So these vortices here and these vortices here, and they're also more sort of spread out in some sense. And you can see that as the time progresses, there is more and more vorticity which is being generated, and the quality of the approximation suffers, right? So if you focus on the picture here, in the beginning, this was less blurred than this guy, but here, for instance, these vortices are very sharp, and this is completely blurred. Okay, so this tells us, there is a caveat here, that if you have a very complex solution with lots of vorticity for this particular case, your approximation is not going to be good. And in fact, that is true. If you take a more complex flow, so this is fairly simple flows, which already illustrate the idea. But if you take a more complex flow, like if you have a cylinder and you have a flow past the cylinder, then there is a number called the Reynolds number, which tells you how complex the flow is. And in fact, there is no pin which can do more than a Reynolds number of 500. For water, the Reynolds number is 10 to the power 7. So 100 million, between 10 million and 100 million. So you're far off. And there is a mathematical, or there is a good reason for that. And the reason is that in this case, the solutions of the PDE themselves are fairly complicated. So somehow this is something that one should always remember instead of blindly applying these methods. This is another example which tells you some of the caveats that are there, and let me explain it quickly, and then we go into the break. So this is the viscous Burgers equation. It has both transport, so this is nonlinear transport, this term, and it has diffusion. So this term is diffusion. It is like the heat equation, right? So if you did not have this quantity here, this would be just the heat equation. But the whole point of transport is that it forces things, nonlinear transport, so some things move faster than some other things. So things get compressed. In some sense, this measures compression, whereas diffusion does the opposite. If something is compressed, it takes it out, right? So this is the basic idea. Now you can do the same arguments as before. You can get an estimate on the total error, which behaves on the training error, which behaves on the number of quadrature points, and which depends on these constants. And these constants, just like in the Navier-Stokes case, they depend on the gradient of the velocity. And the point is that the gradient of the velocity, we know some estimate on it. We know we can measure it in some sense, we can estimate it. And the gradient of the velocity, unlike the vorticity, the gradient of the velocity, we know that it behaves like 1 over square root of this nu, which measures the strength of the diffusion. So if nu is 1, this is order of 1. But if nu is 10 to the power 8, then, or minus 8, then this is 10 to the power 4. It's a large number. So in principle, as nu goes to 0, you could have some blow up of the solution or of the approximation. And I don't know if you can see it, but you actually see it in practice. So if you take nu to be a small number, 10 to the power minus 3, you can go all the way to 10 to 0 or 10 to the power minus 8 for that matter. You can see when it is 10 to the power minus 3, the square root of that is still a manageable number. And that is a very good approximation to the exact solution. But as soon as it is 10 to the power minus 8 or 0, this really blows up, as you can see here. The quantity really blows up. So the pins in this formulation, they cannot approximate this solution. You see that there is a total failure here. And just to further sort of justify our considerations, if there is another mode where the nonlinearity causes what is called a rarefaction, means instead of a compression, in that case, the derivative doesn't blow up and pins can do a very, very good approximation. Because whether nu is 10 to the power minus 3 or 0, you can see that the error actually decreases or is reasonably small. So this is more or less constant error. Here, on the other hand, it blows up, right? So this tells us that one has to be very, very careful when you use pins. If the solutions become complicated, like for instance, the gradients grow or it becomes more vortical or helical as one could use, then the solutions themselves are so ill-behaved that it gets reflected in the errors of the pins. Okay, so this is an important caveat. Of course, there are some alternatives, but this is not the time and place to do it. Okay, so let me just give you a very quick summary, and then after the break, we'll sort of take it up. So essentially, the point is that for a generic PDE, let's take this guy here. For pins, we have more or less some good theory, some rigorous good insight, and a rigorous error estimate, which morally goes like this. The difference between the ground truth and the best approximation that we can do depends on three things. It depends on the number of quadrature points. This is always something that we can make small. For instance, even independent of dimension, if this is random points. So this is a good thing. This is a good term. But there are two terms here that could be problematic. First one is this one. So depending on the PDE, this term can be large, right? And as you saw, this can lead to some failure modes, because if the solution is more vertical, if there are more complicated things happening, then you might have a failure. And the final term that we have not yet done anything about is the training error. So this is still a question, right? So this term depends on the PDE, this one here. But if you look at the training error, this is still a question mark. At the moment, I have even said that it's a black box, right? And after the break, all that we know is from these general considerations that the global minimum, and this is an important point, that there's a global minimum is as small as you want, depending on the size of the neural network. So there is a global minimum which is going to be small. But can we ever reach that? Because remember that at the end of the day, even for the smallest networks that we saw, so I don't remember, let's take one of the concrete examples here, right? So the network size is that there are 8 layers here, 8 layers, 20 neurons in each layer. So the number of weights and biases is roughly 400 per layer in some sense. We have 8 layers, so it's let's say 4,000 roughly speaking, because there are also some output layers and so on. So it's 4,000, small network, fairly small network, but you can see that it's still a 4,000 dimensional problem, right? So in these 4,000 dimensions, you have to optimize a loss function. And the question is, there is a global minimum somewhere, which is going to be small, but we have to start somewhere, which as Ben has already taught you and you saw in the tutorials, we essentially start randomly, right? So we start we initialize things randomly. Can we ever reach the global minimum? Because everything relies on that, because unless until we reach a small or even a good local minimum, we don't have to reach a global minimum. If we reach a good local minimum, then as long as the PDE is nice, this error is going to be small and we are in business, right? And this is what we saw for many, many problems, that we could reach a good local minimum. For instance, otherwise, how would we get 2% error? And also you saw this for these problems here, that the training error could be made fairly small. In fact, even in 100 dimensions, you would have training errors like 10 to the power minus 3, right? So in those problems, you could see that, but can this be done in general? So this is still a challenge. And after the break, let's take a break now. Yes.
It's fair to say for fluid dynamics flow that when you mentioned the quake flow, when you have a laminar flow,
Yeah.
It's working, or do they struggle with the laminar flow cases?
Yeah, it depends on the Reynolds number, because you can also have laminar flows for very high Reynolds numbers, but they do struggle. They can struggle, but they are much better at laminar flow than at turbulent flow. So there is that possibility. Okay, so let's gather here at 1:15 and then we resume the lecture. So I should just pause the recording. Yeah. Also to everyone on Zoom, we are restarting now. So as I said before the break, so the key point is essentially I was telling one of your classmates during the break that for many different PDEs, of course, this term that I'm highlighting here could be problematic, but for many other PDEs, particularly for linear PDEs, this term is very mild. It means it does not even depend on you. So this, let's say, is an imprint of nonlinearity. This is only true for nonlinear PDEs. If it's a linear PDE, it's independent of U and U theta. So in that case, as long as we can train well, and if you have sufficient number of vorticity points, we should be okay. So, but as I said before the break, so the training error is a black box, and let us try to open, let's see if this black box can be opened, and you'll see that at least we can open it a little, not entirely, otherwise somehow the machine learning problem would be solved, which is far from the case. So let us see, let's try to unpack the black box a little, okay? And it's based on a theoretical framework that was proposed very recently by some of us here. So this is the paper, maybe the paper can be uploaded if those who want to look at it. I'll just give you a very, let's say, easy version of it, perhaps even a dumb version of it, just so that we don't get lost in the details, right? So essentially, what is the problem of pins or physics-informed training boiling down to? So the problem is that you have, of course, a loss function. And I have taken a remember that our PDE is du equal to f. This is always the case. So our loss function is given by just L2 for simplicity, because then it's easier to do some of the calculations. So you have, this is the loss function, and you have to minimize this loss, right? So you have a neural network, U, which is dependent on X in this case. X can be both space and time, is dependent on parameters theta, and you need to select these parameters theta, right? So to select these parameters theta, what we use is gradient descent. Stochastic gradient descent, Adam, BFGS, whatever, but they're all in some sense, some variations, some more efficient variations of gradient descent. And gradient descent is a very simple algorithm, which tells us that you stand at a point, you look where, this is what we do if you have to go down, you look where there is a negative gradient and you just walk in the direction of the negative gradient. And hopefully you will find the minimum. In general, it can, if it's a convex function, it will be the global minimum. But these functions are far from convex. I think Ben showed you some of the loss landscapes of these functions, and these are lots of hills and valleys. But hopefully we can find a good local minimum. And gradient descent has some other very nice properties, that structural properties, which make it useful in the context of machine learning. And also this algorithm can be done in any dimension. So whether it is 4,000 dimensions, like the pin that I showed you, or the largest LLMs that are out there, which are closing towards 1 trillion dimensions, the principle is exactly the same. So you have to compute the gradient with respect to the loss, and you have to move in the direction of the negative gradient, right? So this is the algorithm. So the iterate at k plus 1 depends on the iterate at k, and the gradient at the iterate at k. Okay, that's all, with some learning rate, and this learning rate is usually typically small, right? Okay, so now we need to understand and remember that there's a big difference between this problem and the traditional supervised learning, which is what you would use, for instance, to train an LLM. In traditional supervised learning, the loss function here would be some integral of u minus some u theta minus some ground root, u bar, some labels, right? But in this case, we don't have that. We don't have any labels, so we have to infer everything from the PDE, which is given here. And you'll see that that leads to tremendous differences in the way we learn. And let me try to explain a little. As I said, I will have to dumb it down because I don't have the time for all the details. If you're interested, you can talk to me later or you can read the paper. So the first thing we do is that instead of working with the parameters, so this theta, the weights and biases, we look at what happens to the function during training. Because after all, at the end of the day, we have a neural network, and we want to see how this neural network behaves during training, how it is updated, what are the dynamics of the neural network. So this you can say is NN dynamics during training. Okay, so let's start at a point theta 0. So of course, theta 0 is where we start the descent. And then let's say that at least we're close to the theta 0. Then we can do a Taylor expansion. In fact, whether we are close or far, we can always do a Taylor expansion. So we do a Taylor expansion in theta. So theta k is the value at theta 0 plus the gradient, of course. So the gradient with respect to theta. Remember the gradient with respect to theta is an important quantity because it also comes in the loss function. Then the distance from the iterate. So this is the distance from the iterate. And then the remainder term. And the remainder term depends on a second derivative. So it depends on the Hessian. So hk is nothing but the second derivative. So this is the gradient squared of with respect to theta of u. So this is the Hessian of the function. So this is the quadratic term. And of course, you evaluate it using the mean value theorem so that this is an exact inequality, right? This is an exact identity. So in principle, you can rewrite gradient descent just by reordering. So this is a long calculation, but essentially you can rewrite it in the following way. So this is around initialization. So maybe perhaps I highlight this a little bit. So what happens is that around initialization, so this is essentially doing some algebra, you get three kinds of terms. So one is, so in all these terms, what plays a big role, as you can imagine, is this PIs. So this is sort of the tangent directions. So you take u, the function itself, and what is the gradient with respect to theta? This tells you how the function, what is the tangent direction at a certain point, right? So these are the tangent directions. Sometimes they constitute what is called the neural tangent kernel. You'll see that in the second slide. But essentially, these are the tangent directions. This is what is called a Gram matrix. This is very intuitive why this happens, because all that we have to do is we have to compute the differential operator applied. So remember that I take this Taylor expansion and I just plug it in, right? Because this will tell me what happens at the Lth iterate or the kth iterate. And when I plug it in, there is some term which is dependent on theta 0, doesn't change during training. Then there is some quadratic term that we call as the remainder term here. This we are not going to unpack. But the linear term is where the action is. So in this linear term here, you can see that some of these terms are going to come. But essentially what it tells you is that the iterate depends on some quadratic terms, remainder terms. It depends on theta k, which is the current value. And this is where this Gram matrix comes in. And it depends on theta 0 because you're starting at theta 0, you're doing a Taylor expansion. So this kind of a, what is called a simplified gradient descent, I think I call it as a simplified gradient descent. So this is an exact characterization. We've just used Taylor expansions and we have sort of unpacked or unrolled the different terms. Okay, the details are not important here. They just come from the structure, the algebraic structure of the problem. What is important is to remember that this is sort of a Gram matrix. This is a structure of a matrix. Okay. Now, as long as this error term is small, and I will tell you exactly when this error term is small, then gradient descent is what approximated by what people can sometimes call as simplified gradient descent, or some other people call it as lazy gradient descent. There are different names to it. It just tells you that at least locally, when you're not far, then gradient descent can be done much more simply. So in the sense that it depends on theta k, in terms of this matrix, you can say this amplification factor, and in terms of what happens at theta 0. Okay, so what happens at theta k, you make a small increment and you stay close to theta 0. And the smallness of these terms, so this epsilon, so essentially this is a linearization assumption, right? Because I'm saying that this quantity is small. Now this quantity measures the second derivative, the Hessian. If the Hessian is going to be small, the function has to be approximately linear. So think of it as a linearization assumption. It doesn't mean that it is always satisfied during neural network training, but at least near initialization, this is typically satisfied. And that is what is called the NTK, or the neural tangent kernel regime. So this is called the neural tangent kernel. Again, the details are not important here. All that you can think of is that we are starting training. We are moving a little bit along some small directions. So essentially, this phase is going to be linear. So under these assumptions, you can actually compute exactly whether there will be convergence or not. So let's say that you are close to a local minimum, how fast you converge. So in that particular case, this is a very simple matrix equation. So you can just do some algebra and you get this expression here. And this expression tells us that the speed of convergence, okay, there is convergence because these quantities are less than 1 in some sense. This condition number is always greater than 1, so this quantity is less than 1. But depending on how close this is to 1, you will have different rates of convergence. For instance, if it is a very, very small number, then it's very close to 1, then you'll have very fast convergence. If it is relatively far away from 1, then it will have very, very slow convergence. So this is the point, right? And the number of steps that you require to get an error of delta is logarithmic in delta, as you would expect. So you have some sort of exponential convergence, but there is this factor here, k of this matrix A, and this k, from those who know some numerical analysis, this is what is called the condition number. Okay, so remember that this is a matrix. This is a matrix which takes this tangent directions. This can be explicitly computed in some cases. It computes the differential operator on these tangent directions, takes an inner product of them, and then essentially this gives you the conditioning of this problem. So at least near linearization, if or near a local minimum, if you initialize near a local minimum, all that it tells us that you can do it fast or slow depending on how well this problem is conditioned. So your training can be expensive or cheap if this condition number, for instance, if this condition number is very close to 1, let's say that this is very close to 1, the C is like 1. So this quantity here is very, very close to 0, which means that it goes, the number of steps is going to be very, very small. Let's say this is close to 1, so it's essentially exponential. But if this condition number is 1,000, then you are in trouble, right? Because then this is going to be 0.001, or the number of steps is at least going to be of the order of 1,000. So it gets very, very expensive. The good thing about this formulation is, under certain assumptions, which one can argue, and you'll see some examples of that in a bit, you can quantify how quickly we can converge to local minimum. Okay, and the answer is that it completely depends on the condition number of this matrix, of this quantity, which looks a bit obscure here at first sight. But actually, this matrix is not completely obscure. It has a very interesting, let's say, manifestation or very interesting interpretation, because it is related to the differential operator. So this is the differential operator. Just think this could be the Laplacian, this could be the heat equation, this could be the wave equation, whatever. This is the sort of family of this differential operator. And then in function analysis, in PDEs and so on, there is an object which is called the Hermitian square. It is like applying this differential operator twice, okay? But except that this D star here is what is called the adjoint of a differential operator. It's just a generalization of matrix. So remember that if you have a matrix, you know what is the transpose of a matrix. Similarly, if you think of an operator is nothing but an infinite dimensional matrix, then the adjoint is nothing but a suitable version of the transpose. Inside, I don't have to define it. I'll give you some examples and then you'll see what this operator is going to be. Okay, so then you introduce this operator, which is given by this calligraphic A, and this is called the Hermitian square. And it turns out that this matrix here, this Gram matrix, which is written here, which tells you everything about the training, at least near initialization, this is related to this Hermitian square. Okay, in fact, it's a very simple calculation that it is related to this Hermitian squared. There is some, because this guy is a matrix. So this is, if you remember, this is the Gram matrix. Gram matrix, or Gramian, as some people call it. This is the Hermitian squared. Of course, this is an operator. This is a matrix. So in order to pull it down from infinite dimensions to finite dimensions, we use some kernel functions, but that's essentially a detail. So all that you have to think of is that my training depends on the condition number of a matrix, which is morally equivalent to, morally the same as, the condition number of an operator. And this operator is not the differential operator itself, because that is okay if it was a differential operator. It is it's adjoint applied to the differential operator, or what is called the Hermitian square. So let me give you some examples. So the simplest example is if you take the Poisson equation, then D is the minus Laplacian, right? But unfortunately, or not unfortunately, but in this particular case, minus Laplacian is a self-adjoint operator. So it's adjointed itself. So you apply essentially minus Laplacian to the minus Laplacian, and you end up clearly with a fourth order operator. This is called the bi-Laplacian. Okay, so this operator is called the bi-Laplacian. And it sort of, it comes up in elasticity equations. Those who have seen structural dynamics, structural mechanics might have known this. So this measures somehow, so the Laplacian essentially, the second derivative measures the curvature. But now this measures higher geometrical quantities in some sense. So this is the bi-Laplacian. And this makes it, this makes the condition number very, very bad because, okay, this is very easy. So if you take a square or if you take 0 to 1, okay. So let me just give you a little bit of facts here. And you take the minus Laplacian. So the eigenvalues of this, because that's what we are looking for. The eigenvalues of the minus Laplacian are given by essentially k y squared. Okay. So this is roughly the eigenvalues, which means that the scaling between the minimum k can be from 0 or 1 to k, capital K. The scaling between the maximum eigenvalue and the minimum eigenvalue grows like k squared, quadratic. Okay, so the condition number is not very nice, but at least it is going to be quadratic. And we could have managed if that was the case. But for the bi-Laplacian, the condition number, the eigenvalues of the bi-Laplacian, and this is sort of the problem, you can easily calculate it. It's not hard. This scales as a fourth power, as you can imagine. So now the condition number grows like a biquadratic, right? So instead of a quadratic, it's a biquadratic. So you can just imagine that if my problem has 4 modes, let's say, now k to the power 4 to the power 4 is a very large quantity, right? It is 256. And if the condition number is already 256, 1 minus 1 over 256 is a relatively large quantity in some sense. And then the convergence is accordingly slow. You need at least 256 steps, but this is a very, very rough calculation. But if you remember, I think Ben showed you some examples where the problem has oscillatory structure. It has like, I don't know, 10 modes. Then you're finished because 10 to the power 4 is 10,000. So you need 10,000 steps of gradient descent. But this is a very ballpark calculation, but you need 10,000 steps of gradient descent to be anywhere close, right? And this is not very satisfactory. So this is a very negative thing. And this tells you that, first of all, this can be very high. And this is the very nature of the beast, that the high order derivatives are worse conditioned than low order derivatives. And because we are forcing the differential operator, your condition number is twice in some sense that of the differential operator. And this is the key difference, because if you had supervised learning, this is if you train with respect to labels, then this D, the differential operator in that case would simply be the identity, right? The differential operator would be the identity, and the A would be identity composed with identity, which would be simply identity. And there, the condition number would simply depend on the condition number of the neural tangent kernel. Okay, it's not always 1, but it's a relatively nice number. Here, on the other hand, in addition to what would have happened with supervised learning, you get this additional factor here. And this additional factor, which depends on the differential operator, which is endemic to all physics-informed learning, this will tell us that, okay, this problem is not well conditioned in general, particularly if the number of modes in the problem are large, right? Because if there's only one mode, the condition number is just 1. There's only one eigenvalue. But if there are 10 modes, for instance, the contrast between the maximum eigenvalue and the minimum eigenvalue can grow very, very rapidly. And this makes it hard to learn problems which are oscillatory. And I think Ben showed you some examples of that. Okay, the first lesson that you learn from this is that training physics-informed neural networks is a beast by itself. And remember that if you train it, if it's a linear problem like the wave equation, heat equation, and so on, you're done. But training itself is a problem, because this is where this point really comes in. So you cannot work with, okay, I'll teach you something about preconditioning. But the point is that you cannot directly work with with training as it is. So you cannot directly work with gradient descent. Okay. What you have to do, and this is because of this ill conditioning. Okay, so this is a very, very important point. So are there any questions also from people on Zoom about what constitutes the difference between training in supervised learning and training in physics informed learning? So math is not important. What is important here is the concept that you are changing something, you're changing the nature of the problem, and by changing the nature of the problem, you're introducing a factor, an amplification factor, which depends on the number of derivatives that you have. So if you have a third order differential operator, then you will have sixth order derivatives and your problem will scale up. You have a question? Yes?
Yeah, it's possible to use also precondition as we do in methods.
This is precisely what the next point is, right? So I will tell you that in a second. But you have sort of guessed my conclusion. But on the conclusion itself, that there is a difference. Is this point clear? And this is where it will come repeatedly, even when you do your exercises and you see that, oh, it's not training well. Maybe it's not your fault. You see, maybe it is. Maybe it is not. This is where you have to understand, is my problem complicated enough? Because that depends on the, but if it doesn't train, maybe there is something intrinsically wrong with the method itself. And whatever I do, it's not going to work. So you have to make that judgment in a particular application. You have to see whether how many modes are there, what is the differential operator, what is the underlying physics, how well can I train, okay? Because once you train, if the PDEs are relatively simple, you generalize, but you do well. Now, how can we change this? Or are we stuck with this problem? Of course, this is a big problem. So are we stuck with this problem? Not necessarily. There is no general solution, because as you see, all these things are very recent, right? So this is probably the most neatest way of identifying the problem, but other people have identified similar problems. So let me explain at least one general, let's say, procedure, general framework in which this can be corrected, which is through the concept of preconditioning. And for that, I need to add the page and write a little bit. So what is the preconditioning that your classmate just referred to, right? So if you remember gradient descent is theta k plus 1 is equal to theta k minus eta of gradient of the loss function, okay, L of theta k, something like this. And the problem here comes from essentially the loss function, right? So the point is, can we do something? Can we change the gradient descent in some sense such that the condition number improves? Because everything now depends on this k of a. K of a was this k of t star d, right? So this is the condition number of the operator morally. Although the math is a little bit more complicated than that. Morally, it is just d star d. So what you can do, of course, is you can use a traditional idea from numerical analysis, which goes by the name of preconditioning. So preconditioning comes from numerical analysis. It essentially tells us that we should pre-multiply the matrix before inverting a matrix, where the same kind of considerations come when you do numerical linear algebra. So if you want to invert a matrix by whatever numerical method, direct method or iterative method, if the matrix is poorly conditioned, if there's the aspect ratio between its entries or its eigenvalues is very large, then it's harder to sort of invert it. So what you do is that you multiply approximately with its inverse, invert that thing, and then remultiply. So preconditioning is a very simple idea. So essentially all that you have to do is that you have to rewrite gradient descent by doing, let's say, eta of some j of gradient of L. So you modify a gradient descent by adding this precondition. So this object here is called a precondition. Preconditioner. And morally, this is, of course, the math is not that easy, otherwise the problem would be solved. Morally, J has to be essentially A inverse. Okay, so morally these things have to be A inverse. So then the sort of the condition number of JA, because J is outside, A is inside. So the condition number of JA roughly will be close to identity, close to 1. So this is roughly the idea, that you have to somehow know what this A is. You have to compute this gram matrix what you can compute this Gram matrix. It's a pretty heavy matrix to compute. Where is it? It's a pretty heavy matrix to compute. But if you have an operator-centric perspective, you somehow know the operator. But this is a large matrix, right? Because remember that let's say we have 1 million parameters. Then this gradient here is vector with 1 million dimensions. I'm assuming that the output is scalar, so it's a vector with 1 million dimensions. So then you can imagine that this is a very, very large matrix. So it's not that easy to work with it. And there are some techniques which are slowly coming in, but I'm not going to belabor the point here. So essentially preconditioning is either by using the direct form of the matrix or by using some knowledge about the operator, or you try to multiply a prefactor, a preconditioner to your gradient descent such that you have an approximate inverse in place. Okay, so this is roughly what preconditioning is. And this is what essentially it boils down to. So in fact, I think Ben also mentioned this. He had this domain decomposition method, finite basis pins, and so on. So in the same paper where we proposed this theoretical framework, we showed that almost all the techniques that are there to accelerate the training of pins, because this is acceleration, right? If something takes 10,000 steps and you can do it in 100 steps, you accelerate the training. This can be viewed in terms of preconditioning. So essentially, some form or the other, this idea comes in, okay? But let me give you a few examples and then we sort of close the chapter here. So this is a very simple example where already the failure modes are very clear. So this is just a Poisson equation in 1D. So you have boundary conditions, 0 boundary conditions. Maybe it is between minus pi and pi, but okay, that's a minor detail. So you have the second derivative, you are given this matrix here, and of course the solution is sine of kx, right? Because when you differentiate sine of kx twice, you get minus k squared. Okay, so sine of kx, very, very simple problem. We don't need a pin to solve it. We can just solve it by hand. But nevertheless, what happens if you take a pin? So if you take the condition number, in fact, I take an even simpler model. I don't even take a pin. I don't even take a neural network. I take a very simple model. So my u theta is going to be what is called Fourier features, parameterized Fourier features. So this is like a light neural network. So you have AK sine or AL, let's say, sine L pi x plus PL cos L pi x. So these are what are called Fourier features. I think Ben also introduced them at some point. And all that you do is that these are your training parameters. Maybe there is an additional layer. So you can think of a very simple neural network. I don't even want to use neural networks here because you can think of it as sine active. You can think of it as a linear layer, a sine activation function, and then an output layer. Right? So you can think of it in those terms. So if you just take Fourier features, means this is a very light neural network, then you can see that condition number, you can explicitly compute the condition number in this case. For this problem, you see how it grows. Means as k grows, as the number of Fourier features grows, this thing here, or L here grows, this thing grows quadratically, right? So because it grows quadratically, you need lots of, and it already becomes very, very quickly 10 to the power 8. I can't even see 10 to the power 8. So 100 million very, very quickly with just a few modes, right? 100 million, and of course 1 over 100 million is a very, very small number, which means that this whole thing goes very, very slowly. You need lots and lots of steps. And this is also very clear when you do the training, because if you just take the naive version of it, which is here, so these are the number of Fourier features, it doesn't really matter. The loss function is of the order of 1,000. So this simply doesn't train, you see. Of course, if you have just 5 modes in the problem, then it trains. But if you take 100 modes, it simply doesn't train. So the same question happens with neural networks. They perform even worse. The diagrams, the graphs are in the paper. Okay, so what does this tell us? That even for a very, very simple problem, I don't need to solve this using neural networks or anything, right? I can solve it by hand, and I can certainly solve it with finite differences. This physics-informed training simply doesn't work for high modes. So it has this poor spectral behavior, which is associated with the fact that you have this biquadratic growth of the, and you can see that, right? Because this is 10 to the power 2, and remember that it grows like biquadratically, and that's why you get 10 to the power 8, right? Of course, you are out. So this completely matches the theory. In this case, preconditioning works very well because you know what you have to divide. So you just have to divide with L squared because you know how much it grows. So L squared here, and because there is a square, so you get a L to the power 4th that cancels out. And then of course the condition number is 1. This is trivial more or less. Condition number is 1, and the training with how many steps is this? 10 steps, you get 10 to the power minus 15. Okay. So this example was chosen in such a way that you don't need to, the preconditioning here, everything is exact, preconditioning works exactly. This is a very simple problem, of course, and a very simple neural network model, not even a neural network model, a Fourier feature model. But the idea is very clear, and you can't solve this with neural networks. It's such a simple problem. If you take k to be 100, you can't solve it because the condition number is so massive. Okay. So is that clear? So this is, and I will show you an example with neural networks in a second. So no chance because of the intrinsic nature of the physics informed training. So this is with neural networks, I think. Let me look at the distribution of eigenvalues. Neural networks, these are genuine neural networks. I think shallow neural networks, one layer and damage hyperbolic tangent function. And essentially, you have lots of zero eigenvalues. This is well known. But the point is, if you don't precondition, then in this case, okay, it's not as bad. If you take 500 epochs, then you get a loss of about 10 to the power minus 3, which is what it is. But if you precondition, that is, if you multiply the inverse of this matrix, so essentially you take this, in this particular case, it's small enough that we can calculate this explicitly within a few epochs, with 100 epochs, for instance, or less, you get 10 to the power minus 5 in five epochs. So essentially, even for neural networks, this problem works because of this point about preconditioning. So this is a very, very simple problem. And this is another very simple problem where you can see that it doesn't work. Okay. So this is ut plus beta of ux, advection equation, a wave equation, but with only one advecting wave. We know what the exact solution is. U of xt is nothing but u bar, the initial conditions, x minus beta t. And now everything depends on the speed of advection. So as fast as you move. And in fact, you can explicitly compute. So if you take Fourier features, the same examples that I gave you, then you can explicitly compute that the behavior is like, it is with respect to beta. It rises with respect to beta. It is, and you can see that for beta equal to 30, for instance, this is already 100,000, so it will require 100,000 steps, which will mean that it will never train. And this is indeed the case. It never trains, and you see that. So for instance, here is an example. So if you take, for instance, Fourier features, no preconditioning, the naive version of Fourier features, this is how the exact solution is. So beta is equal to 30 pi. So this is a high number, but okay, so what? So this is how the solution behaves in space-time. So this is space between minus 0 and 2 pi, and this is how it behaves in time. So you have waves that are moving, but here it simply doesn't work at all. Maybe in the beginning there is something, but as soon as you go further, you see complete noise. And the same if you take a neural network. If you take a MLP, you don't see any behavior here because we know that the condition numbers are going to be very, very bad, right? Because when it's 30K, the condition number is like 1,000,000. So it will take 1,000,000 steps, and we can't afford 1,000,000 steps. We have taken 1,000 steps or something. But then, of course, if you precondition, and in this case, you know exactly how to precondition this, you just divide with the right quantity, then it works like a charm. So you can see either here, that the loss within 50 epochs, it's already at machine precision. So this works quite well. And and you also see it here, that even if the speed of advection is large, you see that this failure mode has been addressed. So preconditioning really works for this simple problem. And we leverage the fact that it's a simple problem. We know everything about it. We know exactly how the condition number behaves, what the gram matrix is, and we could analytically invert it. The same thing works also for neural networks, means again, the same story. that if you take beta 30 or 10, the loss simply doesn't go down. It's of the order of 1. Whereas if you precondition it, then you start seeing that this goes down. Okay. So within 200 epochs, it's already at 10 to the power minus 6, which is quite good. And you see the same here. So this was without any preconditioning, right? Doesn't work except in the very beginning. And with preconditioning, it works very, very well. But again, as I emphasized, that this can only be done because we are able to have an explicit structure of the problem. For Navier-Stokes, for complicated problems, we don't have access to this exact preconditions. And approximation, people are still doing it, means it's by no means ready. Okay, so I think that's more or less what I have to say. Let me go back to the summary. So essentially, what I tried to do in the second half of the lecture very quickly was to try and open this black box, essentially through a simplified gradient descent. But I think it also told us the story, what we needed to do. And essentially, training is ill-conditioned. This is the main problem. It's ill-conditioned because it depends on the condition number of D star D, essentially. And D itself, as I just imagine that if you take the Navier-Stokes equation, it has some nonlinearity, it has some transport and so on. And when you take D star D, first of all, you get fourth order derivatives, you get space-time derivatives, you get all kinds of cross terms, and we don't yet know how to precondition these kind of problems. And for simple problems, we can precondition them. We can precondition the bi-Laplacian, for instance. We know how to do it from classical numerical analysis. From general linear problems, I think we can do it. For nonlinear problems, this is completely open. So essentially, it says that if you don't have complexity in your solution, either through the PDE or through the data, you can use pins. But as soon as there is some complexity, lots of modes, lots of vorticity and so on, either the training will fail or it will fail to generalize. So one should be very, very careful with these methods. Okay, so I think I finished a bit earlier, but just 5 minutes earlier. So if you have any questions, I'll be happy to answer them, also from people from the chat. Otherwise, from the next lecture, we realize that these methods, they have a lot of promise, but they also have enormous limitations. As I just showed you, even for a Poisson problem, they don't work. So what's the point in some sense? So we have to change perspective. And we are going to change perspective in the next lecture. And since the PDE alone can't help us, we have to rely on data. Okay. And that's going to be its own challenge, but this is what we're going to do in the next lecture. Okay, if there are no questions, we meet on Friday.